Hi, everyone. Thank you for coming to my talk, I guess. It's always a pleasure to be here at Bootstrap to tell you about my work, even if, yeah, I'm a bit sad that this is probably the last time of the official Bootstrap workshop, but nonetheless. This time, for a change, I will not be talking about Pythons, but I'm not going too far from the field of confining gauge theories. I'll be talking instead of confining strings today. And this is some work I've been doing together with Alexander Homrich. Still work in progress, but we're very excited to share it with you. So thank you for letting me do so. And since it's work in progress, we very much welcome comments, suggestions, and even some criticism. Good. So what's the idea? We're interested in confining gauge theories, and as you all know, in these theories, flux lines are confined into flux tube, which are small string-like excitations that are dynamical. So those are the confining strings. And, well, we hope that there's a dual description to gauge theories in terms of a confining, in terms of a string theory description. So one of the answers to trying to solve confinement would be to find this dual description, right? So that's like the ultimate goal. So since this is not going to be the usual string theories that we're used to, it's going to be some more complicated story. What people do when we don't know what to do is to do an effective field theory. And we parameterize our ignorance by using some effective description of the theory, right? So the way people have been approaching confining strings is with the so-called effective string theory, and I'll discuss a bit what that means. But the idea is that we just assume that in some regime it's a free string, and then we start adding derivative corrections the coefficients of which we don't know. So this is very useful because it captures many features of the string, and it lets us compare to experiments and so on. But whenever we do an EFT description, we lose information about the UV. So when we do this description, we're just parameterizing strings. We don't really know whether they're confining or what they come from. So in some sense, we forget that they come from say, an asymptotically free theory. So what we set out to do with Alexander was to try to understand some implications of the fact for confining strings of the fact that they come from asymptotically free gauge theories. Okay, so that's the plan of the talk. So let me start by saying a few words about this effective string theory. And the idea is that, so yeah, just to be concrete, I'll be describing pure Yang-Mills in D dimensions, and later on I'll restrict to D equals to 3. So that's the simplest case because there's only one transverse direction. So, all right, so the basic idea is that when the string is very long, it just gives a linear potential. And then the action of the string should just be an ambugoto, which is determinant here in terms of this axis, that are the transverse Goldstone modes of the spontaneously broken translation symmetry. And then after this, there's some corrections that come with a higher derivative of these Goldstones, and with some coefficients like this one here, gamma 3, that are unknown. Okay. So, right, so this is the effective field theory that people work with. And what is this good for? Well, for example, it allows you to compute the energy states of your string. So this holds works very well for long strings. So you can consider a closed string wrapping some non-contractible circle of length r, and then for large R, it's dominated by this formula here that you may remember from your favorite string theory textbook. That comes from Nambu-Goto. And then there's some higher and higher corrections in powers of 1 over r linked to each of these Wilson coefficients. So by comparing this to some, say, lattice simulations, people can measure this coefficient. Okay. Now, if you give this story to the bootstrappers and these collaborators, they'll do what they do, which is to bootstrap these coefficients. And this is what Joan, Andrea, Aditya, Joao, and Pedro did a few years ago, which is to use the S-matrix bootstrap to put bounds on these Wilson coefficients. So what's the idea? Now you have a 2D effective field theory, and you consider, you just forget where it came from, you just have this 2D theory, and consider a scattering problem there. So the scattering problem is, for example, the 2-2 scattering of Goldstones, where you have a very long string, you have two ripples coming together, colliding and going back away. And this process at low energies is again described by this EFT, and it has some corrections, again, where these Wilson coefficients appear. Okay. So now, once you've raised this problem in the language of S-matrices, we know what to do, because the S-matrix satisfies some very nice properties that we all know and love, such as analyticity, crossing, and unitarity. And then by leveraging on these properties and using some clever tricks in complex analysis, one can translate, one can leverage this in order to put bounds on these Wilson coefficients.
So can you say again how they measure this?
On the lattice, yeah, sorry. So the way they do it is they I don't know what I do. The way they do it is so this is the ground state energy over the asymptotic. So this is basically the ground state energy of the string as a function of the radius, and they measure a bunch of points, and then they fit this with this formula. And then by looking at the corrections in 1/r, you can obtain these Wilson coefficients. Now, there's various ways to do this, and actually, Jose is going to tell us about a different way in the next talk. Sort of the question. Good. Okay, so we were here. The idea is that with the asymptotic matrix bootstrap, you can put some bounds. Here I've shown one as an example, these orange bounds in gamma 3 and gamma 5, and the Wilson coefficients have to be about this curve. And indeed, you can people measure this in the lattice, and they nicely compare well with the bounds. They're within the bounds. Yes.
So the bound.
No, I think this is just to show that it's in this direction. Yeah, it's just how they chose to. I didn't make this plot. Yeah. And maybe that's it. That's basically it. Yeah. Anyways, right. Okay. So this is basically the story of the flux tube bootstrap. It was a bit quick, but it's a beautiful story that puts bounds on these Wilson coefficients, and they nicely are satisfied by the lattice, the determinations of these coefficients from the lattice. But I want to emphasize that this leaves something to be desired because these bounds apply to any theory of effective strings. So the story of effective string theory and these bounds are just the requirement that your effective description is so your theory and the worldsheet is a self-consistent theory. But they don't really know, so they apply to confining strings that come from asymptotically free theories, but they also apply to any other theory of strings, say the of recursive vortices in a Abelian Higgs model or cosmic strings or whatever you like. So one question is, could one improve on these bounds eventually by requiring that this theory has to come from an asymptotically free theory? Okay, and that's more or less the motivation that Alexander and I had in mind when we started thinking about this. And so in order to try to address this question, the first thing you need is an observable of the flux tube theory that is controlled in some regime by asymptotic freedom. And by that I mean that in some regime you can just do perturbative computation in QCD that will determine the result. And that's hard for two reasons, mostly. The first one is that it requires a clear map from the worldsheet to spacetime. And that's because we understand asymptotic freedom in the spacetime description in terms of quarks and gluons in, say, 3-4 dimensions. But we want a theory of the flux tube, so the 2D theory. We need to understand how to map one to the other. And then the other issue is that whatever observable we have, it needs to interpolate smoothly from the region where we have long strings, and we can use the effective string theory description, and the region where we're going to input the UV behavior. Okay. So for example, your first guess could be just to directly use the S matrix. And the idea is that at low energies, I just told you that the S matrix is controlled by the EFT. And in the UV, you should, in principle, so in the UV meaning like when these Gaussians are scattering at very high energy, that should probe the short distances of the theory, and it should be controlled by in some way by asymptotic freedom. And there's Zubovsky has some expectations on how this is going to work, but it's quite hard to really pin it down because even though you have a scattering at very high energies, you still have a very long string underneath. So it's very hard to disentangle the dynamics from the block to the ones of the string. So this is not the best observable to make direct predictions from perturbative QCD. Another guess you might have is the torus partition function, which is you wrap your string on some non-contractible cycle of length r, and then you compute the thermal partition function. And again, when the radius is very large, you can describe this torus partition function with the effective string. And as you start reducing the radius, you would hope to reach a region where you can use perturbative, so it hits asymptotic freedom, and you can use perturbative computations. But that doesn't work because there's no smooth limit to the UV. At some point, you hit the Hagedorn temperature, and there's a deconfinement transition, and you just lose the string. So yes, in principle, like when you take the temperature to be very large, you can use perturbative QCD, but you no longer have a string to talk about. So there's no hope that this will tell you anything about the worldsheet theory. So not all hope is lost. There's still something you can do, which is another observable that's a cylinder partition function. And this has the best of both worlds. So I'll try to explain to you why. So the first thing is we need a map from spacetime to the worldsheet. So let me start by the spacetime picture. I'm going to take a non-contractible direction, so a contractified direction of length L. I'm going to wrap two Wilson lines, so Polyakov loops, around this direction. And they're separated by some distance tau. And I'm going to study this correlator as a function of the separation tau. Now, this, I can take, say, a fixed time slice, and I have a quark anti-quark that are going to source a flux tube from one to the other. So the first contribution is going to be a cylinder of the string going around the loop. Now, if you're at finite n, there's going to be other contributions. So for this talk, I'm going to restrict to large n. But if you're curious about what happens at finite n or in one over n corrections, you can ask me later. We have some expectations that you could also push this to finite n. But for now, let's think in the planar limit. So up pure Yang-Mills, and say in d equals to 3 and large n, the statement is that this correlator of Wilson loops maps to the cylinder partition function of the flux tube theory. Okay, where each Wilson loop corresponds to a boundary, a particular boundary for this flux tube. Okay, so that solves problem number 1. What about problem number 2? We need a smooth limit to the UV. So what is this limit? Well, we're going to study, I'm going to keep L fixed. I'm going to change tau. So when tau is very large, I have the effective field theory description, and I can just use that. But I could now take the limit when tau becomes very small, and in this case, there is no Hagedorn transition. And I just go in space-time, it just corresponds to taking the two Wilson loops very close together. Now, when they're at very short distances, asymptotic freedom kicks in, and I can just use perturbation theory to determine this correlator. And so what does this look like? This correlator now goes as e to the minus L of the potential between the quark and anti-quark. So what is this potential? It's just exchange of a gluon, and that gives a Coulomb-like potential. Okay, it could be this plus perturbative corrections to this. So the statement now, since we have a clear map from one to the other, I can forget about spacetime, and I just have my flux tube theory. So to the theory, I compute the cylinder partition function. And the statement is that as tau goes to 0, so in the UV, this partition function should show a Coulomb-like behavior. Okay? So we found an observable where you can directly inject in a very controlled way asymptotic freedom into the flux tube. Now the question is, okay, so what do we learn from here? So the rest of my talk, we will try to relate this new observable to other observables that we already have, and some other new ones that people didn't discuss so much. Okay. Yeah, stop me anytime if there's questions.
So gauge theory, you need to fix also monodropy on the gauge field.
Yes, yeah. So you mean like this Wilson loop? Yeah.
Yeah, like what the boundary condition when you do it. What we could be.
How many times it winds? Or
Not just the F of one Wilson line with the fixed.
Well, I think this is going to be encoded in this boundary condition from the. So it is going to be encoded like in terms of like a G function of this boundary from the. I see this as data of this particular boundary condition. Yeah, we can chat later. Okay, good. So, right. So the point I want to make is that now we have a new object of the flux tube made its appearance, which is this boundary. We need to understand, at least in the regime of effective field theory, how you describe this boundary. And this is again done with yet another effective field theory. So you start, so the statement is that the full action is going to be bulk, and the action of the bulk, I mean the 2D action, so the worldsheet of the closed string before. And now there's a new effective action for the boundary, the one-dimensional boundary of the string. Okay, so the way you should think of this is, first it's a derivational boundary condition, but it may receive corrections. And these corrections can be described again by derivatives of these Goldstones, and they should satisfy some patterns so that it is compatible with nonlinearly realized Poincare invariants. This was worked out in these papers by Haroni and later by Gazelle and collaborators. Okay, and the statement is that now, so the full theory of the flux tube has some Wilson coefficients here in the bulk and new Wilson coefficients, this piece, appearing in the boundary, which are again new observables of the theory. So yes.
Just to understand logic. Is this effective field theory on the boundary supposed to be valid when the two boundaries are close together?
No. It's only when they're very far apart. Yeah. So now I'm describing what. Yeah. Yes, exactly. So this statement here of of Coulomb is when they're very close together, but that will be for the full non-perturbative thing. And then when they're very far apart, I'm going to use the DFT exactly. Thank you. Right. So what do these Wilson coefficients control? Well, one example is the ground state energy of the open string. So the ground state energy of the open string, again, when it's very long, and in one of our corrections, looks like this: the Nambu-Goto contribution, and then some corrections from the boundary and some corrections from the bulk. And noticeably, the boundary corrections kick in earlier because they have fewer derivatives than the bulk correction. So in some sense, from this point of view, they're even more important. And again, people can measure them from the lattice in the same way, where they simulate this ground state energy, and they can just fit. So for example, for 3D SUA and Young-Mills, these are the results. Okay?
It just seem to enter in even powers, right? In the other group, 1%.
Yes, that's right. There is some mismatch. Like some are even, the other ones are odd. That's right. Right. Okay. Good. So the statement is that these are new Wilson coefficients, and one could try to put bounds on them. So just to emphasize again, this is only when the string is very long. Now we need some object that captures the information of the boundary non-perturbatively at any energies. So what I mean is that before we had the S matrix that capture the scattering at any, so the action at any energies, and at low energies it was controlled by the EFT. Now we need a new object that's called the R matrix, or the reflection matrix, which is going to capture at low energies these Wilson coefficients, but it also describes the process, so this action at any energies. Now, what is this object? So this object is the following. We have a long string that ends on some quark. Now I shoot some ripple of the string against the boundary, so this quark, and then it reflects back into the bulk. Okay? So it can be defined in this way with a particle coming in, particle coming out, and yeah, that's how it looks. So at low energies, you can compute it, and it receives contributions both from the boundary Wilson coefficients and from the bulk ones. And again, there's this separation between even and odd powers. But in principle, this is some object. Well, in principle, this is definitely some object that describes the boundary at any energy scale. So right. So once you have this story, you could try to go ahead and repeat the same thing they did for the flux to Bootstrap and try to do R matrix Bootstrap. So first, we need to understand what are the non-perturbative properties of this R matrix. So the first one is analyticity, and it's essentially the same one as for the S matrix. So one common, the plot looks a little weird because I'm plotting in P, not in P squared. So that's why the T-channel cut sort of has come up here. And the reason why it depends on P is because this setup breaks Lorentz invariance. So now it's no longer just S, it just depends on P. But the point, this is just a subtlety. The idea is that it's still analytic in the first quadrant, except for, and it's stopped by this S channel cut, which has contributions in this channel, and the T channel cut that has contributions in the other one. Now it also has crossing, which is a statement that one channel and the other are related by analytic continuation. And the idea is that in this channel, we have this definition that I gave before in terms of an incoming state, an outgoing state, and the boundary running along time. And the other channel, this T channel here, is the one where you rotate your head. And now the boundary is some state that emits two particles going right and left into the bulk. Okay? And crossing is the statement that one is the analytic continuation of the other. And then the last thing that you would need in order to the Bootstrap is unitarity. And here's where things get a little more difficult, because you need to discuss unitarity in each of the two cuts. So in one of them, the S channel, it's perfectly fine in the sense that the initial state is the same as the final state. So the absolute value of the R matrix is still bounded by 1. But if you look at the other channel, now we have B going into this Fox space state. And since the initial and final state are not the same, this absolute value does not have to be bounded by 1 or principal by anything. So yes.
So S is P squared, and you're saying now it can depend on what power.
Exactly, that's what I'm saying. Yes. Yeah, and as it does. Yeah. That's right. Thanks. Right. So since in principle we don't know what this function, so this function is analytic everywhere, bounded here by 1, but we don't know what is bounded by here. And if we cannot bound it here, then there's no hope to use the same techniques that they used in the flux to Bootstrap to put bounds on these coefficients directly. One needs to know what the function is bounded by on this line. Okay. So in order to try to approach that, what one could do is do the obvious thing, which is to follow the blueprint of the form factor Bootstrap. And you just complete the square in some positive semi-definite matrix. If you recall Marco's talk from last week, that's basically what they were doing in the case of conformal boundaries. So what do? I put the K matrix on the off diagonal. So up here, top left and top right. So yeah, whatever, diagonal. And then I need to complete the square with the inner product of B and B. And if you're careful with this, you see that what enters is the spectral density, or the spectral density is defined in this way. So the cylinder partition function, which is BB with some time evolution, is written as an integral over energies of the spectral density. So since this has to be positive semi-definite, you learn that the K matrix squared is bounded by the spectral density, much like happens in form factors. So that's very good. Now I can just go ahead, integrate over energies, and I find this bound. And in principle, I'm very happy. Why? Because I've related two things I wanted. So on the one hand, I have the K matrix, which captures this Wilson's coefficient at low energies, but in general, it captures the boundary at any energy. And on the left-hand side, I have the cylinder partition function, which is what I argued is controlled by asymptotic freedom at small tau. So in principle, we could declare victory. Now we could go ahead and try to do the bootstrap and so on. But that's too quick. It doesn't work because there's a subtlety that I skipped, which is that in order to define the K matrix, you need the length L, which was the radius of the clustering, to go to infinity. Why? Because it's an inner product between a boundary state and a Fock space state. And if you want a Fock space, it better be that the volume goes to infinity. Okay, so what happens then? Well, the issue is that the partition function blows up in your face if you take the infinite volume limit. The reason you can see this by going to the open string channel, and then only the ground state contributes, the ground state energy of the open string, and that's in general negative, so this thing just goes to infinity, and you find that your bound is trivial. It just says that it's upper bounded by infinity. Okay, so that's pretty sad. You could like wrap up and go home because there's no game that you could play. Yeah, sorry.
Isn't there a more kind of obvious issue with just that your low energy expansion is for small p? You're trying to say something about small tau which relates to large p. I mean, how is it that you can expect to?
No, yes, that's right. I'll get there. So I'm not expecting that's absolutely right. So the only hope is that, so indeed, so small tau will be controlled by large p, and the only thing that this will tell me is about the asymptotics of k, so like at large p. But that was to be expected, right? Because in some sense, asymptotic freedom should be the high energies of the string. And then it'll be a second order question how you can use the asymptotics of your K matrix to put to change the bounds on the EFT into like the dispersion of relations or whatnot. But right now we just want to say something, whatever it is, about the K matrix. Yeah, but we cannot even do that because of this issue I was mentioning. So okay, so should we just stop and leave? Well, we were thinking about it for a while, but then we just tried to wonder what could be a possible bound that remains even at finite, I think as you send L to infinity. And we got to this possible candidate. So what are we doing here? The statement is that Z is exponential of something that's extensive with the volume. So log Z is extensive. And here we have something that's directly linear with the volume. So the only thing that you can hope for is some bound such something like log Z bigger than this. Okay, so, and then you would cancel the L's and this is what you would get. Now I want to emphasize that this has no right to be true, which is like, at this point, we just wrote it down. And the reason why it doesn't have any right to be true is because the way this works is Z is written in general. So in order to understand this formula, you should, the way you should understand it is that Z is written as an infinite sum of n particle contributions. So there's 2 particle, 4 particle, 6 particle. Here we've got the 2 particle contribution and everything else was positive. So that's what explains this bound. But as soon as you take the log, this is no longer true, but that all contributions are positive. So this in principle doesn't have any right to hold. Nevertheless, we computed this free energy, this ground state energy in a couple of cases that we could with TBA. So those were integrable models, and this bound happened to be true. So then after some thought, we managed to prove that this bound is true if your flux tube theory is integrable. Now, this point is just a simplifying assumption because we know that the actual flux tube of pure Yang-Mills is not integral. But for now, let me just pretend that it is and tell you how this bound follows from integrability. Okay. So okay. In integrable systems, this ground state energy can be computed from TBA. The details, if you're not familiar, are not important, but the idea is that this ground state energy is written as an integral of some log. This log takes into account the combinatorics of particles. Here appears the K matrix, and then there's something called a pseudo energy. The pseudo energy is the solution to this complicated equation that has the pseudo energy on the left and also here on the right. But the important thing to note here is the kernel of this thing. which is the log derivative of the S matrix. Okay, so this may ring a bell because it's nothing else than Wigner time delay. Okay, so back in the 50s, I believe, Wigner showed with wave packets scattering against some potential that the time delay of a particle, so the time it takes for it to cross some scatterer with respect to crossing that same space without the scatterer is given by the log derivative of the S matrix. And if you're scattering massless particles, you expect time delays to be positive. So why is that? Well, because the two particles come on the light cone, and any negative time delay, so time advance, would push them out of the light cone. And so if they're for massless scattering, the statement is that they always need to come out inside of the light cone, and that will mean that the time delay is positive. Now, this may look too quick, and indeed there's some argument saying, well, there's some debate because you need to take into account the width of the wave packet and so on. So it could be that it's a bit small, like to the uncertainty or of where your position is and so on. So in order to be convinced, what we did with Alexander is to actually prove this, the time delay is positive, just from the usual assumptions of analyticity and unitarity of the S matrix. So now it's a theorem if you wish. I don't have time to walk you through the details. You can ask me later. But just from analyticity and unitarity of the S matrix, the time delay is positive. So end of the discussion. Now, the idea is that now with the fact that this kernel is positive, we can go back to this TBA system and prove our bound. For that, the only thing we need is another assumption, which is that the low temperature expansion converges. And what does that mean? So low temperature, by this I mean long tau. Yes.
So you have an integral model where particles have like finite size, like I don't know, R here.
Yeah.
And like delay is like.
Yeah, no, hard sphere is bad, but as you're telling me, what is a hard sphere? I hit it here, and it immediately feels the repulsion there. So of course that violates causality. So this should be like point-like particles that are like, yeah, it's a fully relativistic system. That's yeah. So it has to be relativistic massless scattering system. Yeah. Okay. So we need a low temperature expansion. What does that mean? So when you compute this TBA, you do it iteratively. You want to do it in a computer, and you start with long tau, and you start adding corrections, and 1 over tau. And the assumption that I told you before that there's a smooth limit to the UV is essentially the statement that this low temperature expansion should converge at smaller and smaller tau. Okay. So what do? You just expand the law, and you see that all the contributions to the free energy from this formula are positive, using the fact that the time delay is positive. So you see that the pseudo energy. So the pseudo energy is upper bounded by the energy of the pseudo energy of the free system. So 2p is just the energy of the two particles if they were not interacting. Okay. So I want to emphasize that this is a bound on thermodynamics from causality of the microscopic scattering. And then you just use this back here. So I expand the other formula, and you go through the chain of inequalities, and they just align in the next direction so that you can prove our bound. And indeed, the ground state energy of the open string in an integrable model upper bounds this integral of k. Okay. Now, yes.
If I write down some phenomenological holographic confining background to some Minkowskian works over some internal space with them, where the place where the long string is stuck, would this bound be trivially satisfied?
Is it an integrable model?
No, not integrable. It will not. I mean, I just write some arbitrary metric of Minkowskian fibered over some internal space, and the warp factor is minimized at somewhere, right? So I mean that's like the typical holographic confining geometry, and and just look at Ambogoto in this background. You think I can? I was wondering whether this kind of bound would be trivially satisfied.
I see. So I'm not too familiar with the example, but is it just Nambogoto or it receives correction from the warping?
To begin with, if I just take a phenomenological model, just take Nambogoto.
Okay. Yeah. So if it's Nambogoto, so there's two questions. So here we assume that the bulk is integrable, so that would be the case for Nambogoto. Well, actually, it depends on the number of dimensions.
Oh no, I mean the Nambogoto in the bulk, not in the Minkowskian.
Right. I understand. So yeah, I don't know. I mean, yeah, the statement is that if you have an integral like 2D theory and an integrable boundary, this will be true.
And especially that if you have some massive resonances, it kind of, I guess, it will further suppress the right hand side.
So no, massive resonances are still okay because they still contribute to a positive time delay. So yes, I guess. Yeah, I mean, it's a question of whether, this bound will not be saturated. It will still receive, it'll be far from being saturated because higher particle contributions will also matter, but it should be satisfied if it's integral. Yeah. But indeed, for for QCD and so on, we know like it's been measured that the flux loop is non-integrable. So you may be like, okay, this is just, could it be an accident of like all the higher symmetries that like this infinite number of symmetries that integrable models have? And yes, that could be, but there's also hope that that this bound actually continues to be true beyond integrability. So let me try to motivate a bit why that hope exists. Yes,
Your tracking is basically out.
damn it.
So if you can.
I'll try to be quick about this. But we had some questions during the.
Yeah, I'm also looking for questions.
Okay, well, you can ask while I speak. Okay, so okay, so what is the issue with beyond integrability? Well, the issue is that the community has not done the homework, and that the formulas to compute this ground state energy are just not there. So the closest analog is this obscure formula from the late 60s by Dashen, Ma, and Bernstein, which applies to the torus partition function. So it's not directly applicable to what we have, but let me just like walk you through it nonetheless. So this just says that the torus partition function of some interacting system is given by the torus partition function of the free system plus this term over here that captures the interactions. And the important thing to note here is the kernel of these interactions. Okay, so this looks very similar to what we had before, and it's none other than the Wigner-Smith time delay operator. Okay, so this is supposed to capture the time delays in a system where you have particle production and even like multi-particle scattering. Although the actual interpretation is still a bit up for debate. So we're still like trying to make sense of what exactly this operator means, but we do expect some notion of positivity for these time delays. The reason being that even if I'm doing multi-particle scattering, it better be that the particles come out inside the light core if I have a causal and relativistic system.
But this energy derivative, what does it mean?
Okay, you always know what to ask, right? So yeah, I mean, this formula is very very formal. You should think of it like, if you wish, this should be the like you choose some frame. It could be the center of mass frame. This is the energy of the states in the center of mass frame. And now you would say, is this frame dependent? Actually not, because you can just change a change of basis changes the frame. So this formula is actually, in principle, could hold for relativistic systems. Now it is true that this formula makes no sense, because we actually go and you try to compute any of these terms, you'll find a lot of divergences that come from forward limit singularities and so on. So going from this, like this is highly formal, is derived at the level of resolvents of the S matrix, but one needs to actually try to make sense in terms of wave packets and whatnot. So that's something that's still work in progress, and there's several groups working on this, but I can just point to that. So yeah, one of the work in progress is to try to make sense of DMB, and that there's these two papers from last year that were precisely addressing these issues of these forward limit singularities in multi-particle terms of this matrix. Now, the one thing that I wanted to emphasize here at this stage is an intuition as to why we expect this type of causality bands in thermodynamics, the same type that I motivated for the integrable cases. And the idea is the following. The idea is that causality requires time delay to be positive, and positive time delays are in general associated to attractive interactions. You can think of this as two particles come in. If the interaction is attractive, they could form some bound state for a while, and then they go out. That clearly is a positive time delay. And then if you have an attractive interaction, that lowers the energy with respect to the free system, and that in turn increases the partition function. The partition function weights e to the minus e with that minus over there. Okay, so indeed you see that in this formula, if this time delay is positive, it increases the partition function with respect to the free one. So that's why we expect this type of bounds on thermodynamics from causality to continue to hold beyond integrability. Now, this still is a bit speculative because of the reasons that I outlined down here. Indeed, one needs to actually make sense of that formula, and that's still, there's some work that needs to be put there. One needs to completely understand and prove, hopefully, the positivity of this time delay beyond the elastic to scattering. And then if you ever want to use this to prove our bound, you moreover need a generalization of the MB4 boundaries. That's something that we're working on.
You know that time delays are in general not positive in general. So what would be the ingredient to prove that they are positive? I mean, what are...
So the ingredient that we used was the fact that it's massless scattering. And so, yeah, massless, so it's massless. I mean, yeah, honestly, so for this one, the proof just uses the fact that it's analytic in the upper half plane and unitary. And that's all you need. So what would be, so here now you
was to three. For instance, in 4 dimensions, you would be able to put in 4 dimensions.
Well, now you need flavors of the S matrix. So I don't know. Yeah, for right now it's just for a simple function as it's analytic and so on. Yeah. I can prove that the log derivative of that function is positive. Yeah. Now you need if you have an operator, you can have flavor. There's some there's some generalization of these theorems that we use here that hold for operators. And I think in the case of 4 dimensions, since it's just like, it'll be a finite number of flavors, then you can probably prove it. But in this case, now this operator is infinite dimensional, because you have 2 to 2, like 3 to 3, and so on and so forth. And then it's a bit unclear whether the theorems that exist for at the level of operators apply to infinite dimensional operators. So that's the obstruction that we are facing here in order to prove this positivity. We have, if the S matrix were a finite matrix, we have a proof, but it's not a finite matrix. So we're working with trying to take the infinite limit and see if that makes sense or not. So that's why, yeah, we don't claim to have a proof yet for that. Okay, and since I should wrap up, let me try to take a step back and see what I've told you. So there's 2 main takeaways that you should keep for when to walk away. So if you were not paying attention, these are the 2 things that I want to emphasize. One is I've told you that there's this new kind of bounds in thermodynamics from causality, and that lead to this bound for the flux tube, which is that the ground state energy upper bounds the K matrix. Okay, and this we proved in integrability. At this point, it's still a conjecture beyond integrability. The jury's still out whether this is true or not. But okay, the other thing I've told you is that the asymptotic freedom controls the UV behavior of the cylinder partition function. And now, if we recall that the radius had to be going to infinity, this has this behavior in terms of the open string ground state, and that means that at small tau, the open string ground state has to behave like Coulomb potential. So let's take d equals to 3. Coulomb potential is given by a log, and with some coefficient that you can just compute from perturbation theory, and that implies that at small tau, this integral of the K matrix, I'm putting the 2 together, integral of the K matrix is upper bounded by a log. So now you can just go through the algebra, and as she was mentioning before, this is controlled by the high energy, so the large P behavior of K, this integral, and we reach this conclusion that in d equals to 3 in asymptotically free theories, as a consequence of this bound, which is true in integrability and conjectured beyond that, the K matrix we show that has to decay as 1 over P with a fixed coefficient. Okay, so this is a direct consequence of asymptotic freedom into an observable of the flux tube. Okay, and just as a teaser, of what this bound can be used for, in particular, can be used for to rule out the critical string theory result. So what is that? So you take the EFT and you put all the coefficients to 0, so that you just keep Nambu-Goto, and then it gives you this K matrix. And it's only the Nambu-Goto contribution, and that is a pure phase. So the absolute value of K is just equal to 1. So it clearly violates the bound in the sense that it does not decay. And so what this means is, okay, this is a K matrix that's perfectly valid from the point of view of the flux tube bootstrap. That's perfectly fine. But if you insist that your flux tube has to come from an asymptotically free theory, it better be that your K matrix decays as 1 over P. But this is not the case, and we would rule out the critical string theory result. Now, of course, that's to be expected because we know that critical strings don't show this logarithmic behavior. But it's nice that now we have a rule that kicks it out. So we hope that by this kind of rules that come from asymptotic freedom, we can focus and push the bootstrap forward and nail down the flux tube theories that come from asymptotically free gauge theories. And now I'm wrapping up for real. So this is what we've been doing, and there's a lot of future directions if this line of reasoning continues to work. And one of them is to independent of the flux tube, we can push for more bounds on thermodynamics from causality. For example, directly on the partition function, not so much on the cylinder. Then we could also try to explore how that relates, and asymptotic freedom propagates back onto constraints on the S matrix, not just on the K matrix. At the same time, we're starting to set up the numerical bootstrap for these boundary Wilson coefficients. And as a final future direction is to use this type of bounds, which have the partition function on one side, or the ground state energy on one side, and the S matrix or K matrix on the right hand side. The way to use something that this formula could be very useful for is to inject lattice data. You see, because in the lattice they directly measure these ground state energies, and then the way they extract these Wilson coefficients by making some fits that are a bit complicated. But now with this type of formulas, you can just inject the results from the lattice on one side and run the bootstrap to constrain the K and S matrix. And then that could be used to measure the Wilson coefficients with some bootstrap bounds, but it could also be used to measure the shape of K and hopefully S, if it enters this type of bounds, at all energies. And that could be a very useful way to leverage this information from the lattice. And with that, thank you so much. Sorry for going over time, and stay tuned for updates.
Okay, since we basically have no more time, I just to ask the next few questions to John.
Sounds good. Thank you.
Why don't you just try to pick? Really nice.
Thank you.
Yep. It's absolutely enough. I mean, it's more than that. Get in the end, understood that in our field, something was like projection, not doing anything.
Thank you.
Yeah,